Welcome to this OST2 lecture about platform configuration registers of a TPM 2.0. This topic was the most requested during TC1101, and we needed to gain some prior knowledge before reaching the PCR topic. So what is a PCR? Unique feature of the TPM. As the name suggests, any PCR is a memory register. That memory register can hold only a hash digest. The length of the digest depends on the algorithm. Typically, PCR registers support SHA-256, and if the TPM supports, for example, SHA-512, then the PCRs should be having banks also for that. SHA-1 is supported across any TPM 2.0, however, this is only for backward compatibility with existing systems, because SHA-1 is deprecated and insecure. What makes PCRs unique? The fact that the content of a PCR can be cleared only under very specific conditions. Usually these conditions are related to power on-off cycles and other limitations that we'll talk in a moment. Because of this, PCRs are difficult to tamper with. This is a quick overview of how platform configuration registers work. We already learned that PCRs are just memory registers that can hold a hash digest. What happens at system boot or TPM power on is that all of these PCRs get reset to either all zeros or all ones depending on their PCR number, and this is defined in the TCG spec, and we'll talk more about this later in this lecture. As a user of the system, there are exceptions for some PCRs when you can perform a reset. The difficulty of tampering with a PCR comes not only from the limitations on when to clear the content of a PCR, but also from the way we can write to the PCR. There's only one write operation available to us, and that's PCR extend. PCR extend is the operation of adding new information to the existing old one and concatenating the two hash digests. This means that the result, the third hash digest, will carry the information from the original old one and will be modified based on information from the new digest that we appended. Together with the inability to clear the PCR register, this means we can only add new information, and the order of adding information, adding hash digests, adds additional guarantees about the value of the PCR. The value of the PCR will be known to us only if we follow the same order with the same hash digest being extended. This makes the PCRs great tool for evaluating device health and system integrity and file integrity and so on and so on. PCR reset is the operation that we use to clear a PCR content. Most PCRs are reset only during power on-off cycles. Some PCRs are reset during power on and only in specific TPM locality. Very few PCRs can be reset at any time, and usually those are for debugging purposes, testing and development. It is not out of the question to use the PCRs that can be reset at any time for application purposes. However, we need to be aware of that other programs can extend information in that specific PCR. As mentioned, most of the PCRs can be reset under very strict rules. So what is TPM locality? There are at least 5 locality levels from 0 to 4 that any TPM 2.0 has. The TCG does not limit the number of localities. However, it is the most common case to see from 0 to 4. The TCG specification allows a TPM to have up to 229 of these levels. So what is a locality to the TPM? We can look at it as levels of access. Depending on the locality level, we are given certain capabilities. In relation to the PCR, this means that we have to be in a specific level of locality to be able to clear the content of that PCR, sometimes even to use it and extend information in the PCR. TPMs start in locality 0. In that level, the TPM expects a command from the platform. At bootup, the platform initializes the TPM, probably performs TPM2 startup, and increases the locality level. Then we're handed off to the UEFI or BIOS. We get another increase in locality. And then we're passed to the bootloader and OS. Usually the operating systems and our applications would work in locality 4. If you're working on an IoT system, however, you might be working in a different level, lower one, with more capabilities. It really depends where leaves the solution, the software that you're developing. You could be a UEFI vendor, for example. Here is a better overview of the different levels and how they're linked to the different stages of the system boot, and also what is the expected software type to use these locality levels. On the bottom of the screen, you can see the so-called extended localities that were added later. Some are reserved, but most are actually available, and depending on the needs, the technical committee of the TCG can decide to reserve additional ones for your use case. In most applications, the existing 24 PCRs with the typical 5 levels of locality are sufficient. At system start, the TPM is in locality 0, and the CPU will instruct the TPM to perform a TPM2 startup. Of course, it is the UEFI BIOS code that will send that instruction, but the host is the CPU that sends the commands to the TPM. In turn, the TPM will reset all 24 PCRs from number 0 to 23. And then the UEFI or BIOS will extend information into the first PCRs, usually PCR from 0 to 7, with important information about the state and integrity of the UEFI configuration and so on. Below, I've added a link to the Linux TPM PCR registry for more information about the real-world usage of PCRs in personal computers. Now let's get back to our example. Because the operating system works in locality 4, the OS could not reset PCRs from 0 to 7 or add new information into these PCRs using PCR extend. This means that the information provided to us from the system start by the UEFI or BIOS into these PCRs is protected until the next reboot, and we can use that in our operating system or during the boot stages. This, of course, falls on the assumption that our UEFI is also genuine and it had successfully passed a secure boot process, or better yet, a measured boot process. And one last note, locality levels can be used in TPM2 policy crafting. We'll talk more about TPM policy in the next lecture. Here is an overview of how locality levels relate to PCRs. Usually, at OS runtime, either in user space or in the operating system in kernel space, PCRs from 8 to 15 are used, because in locality 4, there is no PCR reset allowed for PCRs from 8 to 15. We can extend new data, new hash digest, new information, and it is protected until the system reboots. Going further, here are some real-world examples how PCRs are used. Microsoft's solution to disk encryption and protection of the operating system uses PCRs from 8 to 11 or 11 to 14, depending on the version. The Linux popular bootloader group uses PCRs 8 to hash the kernel command line, and this way it can verify the kernel launch command. Then it further extends the kernel image that is going to load in PCR 9. This means that once the Linux kernel has booted, it can verify the state of the system and see if it's genuine and should continue forward. This also gives us control at bootloader level in group to decide, is the PCR 9 digest matching what I'm expecting to boot and not boot at all? Later, the kernel can verify the kernel command and decide, okay, this is not the command I expected. And this might be because they're trying to boot from a different root FS, and this way we can prevent an attack on the system. This all adds up when we start using the TPM 2.0 to generate signed proofs as evidence of the state of the system. This is usually done using the TPM2 quote command to sign PCR values.